paint.
Okay, I think I figured out how to turn off everybody's bell as they arrive. So I think we're ready to start today's seminar. So today's speaker is Zurab Janelidze from Stellenbosch University, and he's going to speak on Noetherian forms.
Thank you very much. It's a great honor to be giving a talk at this seminar, and it's wonderful that this seminar exists, and thank you so much for everything. So the talk is on Noetherian forms. I'm using Paint, Microsoft Paint for the talk, so it's basically scrolling down, and I'll try to maybe make some annotations as we go along. There are five parts to the talk. They're written out here. There are also collaborators for the different parts of the work. Amartya Goswami, Helmut Podinger, François van Niekerk, and Thomas Wakehill. Okay, so the first part is trying to answer the question, what is a Noetherian form? And before that, we're going to look at the question, what is a form? So a form is a category equipped with an additional structure that specifies abstractly subobject posets. So in general, in a category, you can define a subobject as a monomorphism going into an object. But in a form, a subobject is an abstract entity. It doesn't have to be a morphism at all. So what we have is that for each object X, we have an abstract poset called sub-X, whose elements we think of as subobjects of the object X. And then for every morphism, F between objects, we have a relation between the subobject posets written this way. And so we read it as B is bigger or equal to A along F. It's basically saying that the image of A under F is contained in B. So that's what it will be in the usual examples of forms. So this data is supposed to satisfy some axioms. So the first one is this one over here. It's kind of transitivity axiom. If we have C bigger or equal to B according to some map G, and B is bigger or equal to A according to some map F, then we can combine that information and get C bigger or equal to A. But then for it to be comparable, we'll have to compose the morphisms according to which the other comparisons were made. And so we have implication from left to right. Later on, we also want implication going backwards, but we will leave that for now. And then the other condition is that the relation we have associated to the identity morphism is exactly the order relation in the subobject poset. So another way of thinking about this structure is simply as a functor. If C is the category we've been working with, then the functor will have C as the codomain. And the domain basically will be the category of subobjects. To be more precise, the category of pairs of object with a special distinguished subobject. And so what the functor does, it maps every subobject down to the object of which it is a subobject. And then we have to decide when there is a morphism from A to B that maps down to a morphism F. And if there is such a morphism, we want it to be unique. So the functor is faithful. And the existence of such a morphism is exactly the requirement that B is bigger or equal to A according to F. So the axioms we put forward here, these two, just say in a different way that we have just a functor which is faithful and whose fibers are posets. A fiber would be the subcategory of B that maps to X. So all the objects that map to X, and all the morphisms that map to the identity morphism of X. The reason why it's convenient to have a form as a functor is because then we could take the dual functor. And in the dual functor, we just take the dual categories, B op, C op, and the dual functor. Now, the effect of this at this concrete level is that in the dual form, direction and we will also be reversing the inequalities. So it's just like taking a dual poset. In fact, we can think of a form as a kind of indexed poset in some sense. And so this is the dual poset. Okay, so formal duality is nothing other than the functorial duality. So that's what a form is. Now, the guiding example for what we want to do with this structure is the form of subgroups of groups. So this is when the category C is the category of groups, and sub G, so that abstract information, now refers to the actual poset of subgroups of a group G. And the relation is the one that we hinted on before. So B is bigger or equal to A according to F when F of A is included in B, or equivalently when A is included in the inverse image of B along F. So now in a general form, we want to kind of have this ability to do direct and inverse images. And this can be written out as these chain of equivalences. So we would like to have a mapping that maps subobjects of an object X, that's the domain of F. So think of F as having domain X and codomain Y. So we want to take a subobject in X and have a subobject in Y produced by F. And then also we want to go backwards. And we want then these inequalities to be equivalent to each other, just like in a Galois connection. But moreover, we want them to be also equivalent to the initial relation we've introduced originally, that B is bigger or equal to A according to F. And then the notation would be more convenient if we write the direct image of A under F by just putting FA, and the inverse image by just putting BF, because then these equivalences can be seen as kind of taking the F from the subscript of the inequality and shifting it to the right in front of A here, or to the left in front of B. So in computations, it becomes convenient to have this notation, because then one can quickly see how the Galois connection works there and get some conclusion which with the other notation might have taken a couple of more seconds to notice. Okay, so we also want this construction of direct images and inverse images to be functorial. And this can be written out as these laws. So the direct image of A under F and then under G should be the same as a direct image of A under the composite GF, and the same for inverse images. Now, these two axioms turn out to be equivalent to each other because, as we said previously, this direct inverse image will make a Galois connection, and if in one direction it's functorial, then in the other direction it will be also functorial by properties of Galois connections. But moreover, they can also be substituted with the other axiom we said here, the reverse implication. So if we have this reverse implication here, then we don't need to require these separately. They will come as conclusions of that reverse implication. So if we have a form in which we have these direct image and inverse image maps, and in addition to that, well, they form a Galois connection as we described here. And in addition to that, each poset of subobjects of X is a bounded lattice. So if we have all of that, then we will call such a form an Orion form. And the reason for this is because Ore was the one who studied extensively Galois connections and tried to apply it in developing abstract algebra in terms of subgroup and subalgebra lattices. But we'll come back to some historical remarks later on. Okay, so now how do we get a Noetherian form out of an Orion form? So to do that, we want to equip an Orion form with 3 additional properties that will mimic these 3 properties of the form of subgroups of groups. So first of all, we want to have the lattice isomorphism theorem. And then we want to have the first isomorphism theorem. And then we also want a join of normal subgroups to be normal. In our context, we would carry this over, but also require the duals to be true. which are true in the case of the form of subgroups of groups. But to do that, first we have to define what is a normal subobject in our context. So given a morphism f from x to y, obviously we would define its kernel to be the inverse image of the smallest subobject of y, right? That's what a kernel should be. An object, a subobject that's equal to a kernel of some f will be called a normal subobject. Okay, so now let's look at what is the dual notion to that. So duality reverses arrows. So arrow going from x to y will now be going from y to x. 0, the bottom subobject of the pose set, will become the top subobject. Inverse image will become direct image. And what we get here as a dual construction is direct image of the largest subobject of the domain. And that, of course, is nothing other than the image of f. So in this structure, kernel of f and image of f become dual constructions. All right, so, and then objects, subobjects, which are of the form image of f for some f are called conormal subobjects. So now we are ready to formulate the definition of a Noetherian form. It's an Orion form, so it's the definition written out here. It's an Orion form where we have these three axioms, and these three axioms are translation of these three properties for forms. So the first one is an equational way of stating the lattice isomorphism theorem. It says that if we have a subobject A, we take its direct image by f, and then its inverse image by the same f, that should be equal to A joined with the kernel of f. So this is a property that's very specific to group-like structures and doesn't hold true in general. However, the dual property is something that does hold even for sets and subsets, which says that if I have, now think of it as subsets indeed. So think of B being a subset of the codomain of F. We take its inverse image, then we take its direct image. That will certainly be the same as the intersection of B with the image of F. And to notice that they are duals, we just have to remark that the kernel becomes image under duality and the joint becomes meet, and the direct and inverse images swap around. And so that's how these two equations are equalities are dual to each other. So that takes care of the lattice isomorphism theorem. The second property is the one that takes care of the first isomorphism theorem. So we want every morphism F to decompose as a projection followed by an embedding. Now what is it? Well, and moreover, we want this kernel of this projection to be equal to the kernel of F and the image of the embedding to be equal to the image of F. But how do we define what a projection or an embedding is? It's not enough to just say that E is an epimorphism and M is a monomorphism. We want to say a bit more than that. What we want, in fact, is a universal property that says that if I've got a map E prime whose kernel contains the kernel of E, then necessarily we should have a factorization via a unique map U. So such E prime should factor through E via unique map U. That forces E to be an epimorphism, but not just that, a bit more than that. This universal property will be useful, and indeed that's what kind of hints us to the first isomorphism theorem. So basically this Z appears now here as a quotient of X by the kernel of F at the same time. So I didn't say how an embedding is defined, but it's defined by a dual universal property. So at the same time, Z appears as the image of F, and that's what the first isomorphism theorem is, that the quotient by kernel is the same as the image of the homomorphism. All right, so that's the second axiom. And the third axiom, we can just copy paste that literally. We want, if I have two subobjects and I take their join, if they're normal, we want the result to be normal as well. And the dual property is that meet of conormal subobjects must be conormal. Now, in the case of the form of subgroups of groups, of course, everything there is conormal because every subgroup can be presented as an image of a homomorphism. So the second requirement is kind of trivial there. But this is not going to be the case in every single Noetherian form. An example where this is not the case is the form of additive subgroups of rings without identity. So if we consider as objects rings without identity, and a subobject is an additive subgroup of it, then the normal ones will be exactly ideals and the conormal ones will be exactly subrings. And of course, it's not true that every additive subgroup of a ring is a subring. So not everything is conormal there. But it is true that intersection of conormals is conormal. Okay, so that's the definition of a Noetherian form. And what comes next is description of some examples of Noetherian forms. I already mentioned we had two so far, the group case, which was our motivating example, and the ring case. Now, more generally, one could take a variety of universal algebras that has these terms. So this is a Maltsev condition, which was first formulated by Aldo Orsini. He called varieties satisfying this Maltsev condition classically ideal determined varieties. In the case when n is equal to 1, this condition was studied by Slominski. If any one of you know a bit more about Slominski, I would love to hear about Slominski. I don't know anything about Slominski except I've seen the paper where he introduced that condition. So if I have a variety having these terms, then its form of subalgebras will necessarily be a Noetherian form. But the requirement there is that the variety needs to have exactly one constant. So the 0 there must be the unique constant. In other words, the free algebra of the empty set must be singleton. So the algebra of constants must be singleton. Okay, so there are these kind of structural examples of Noetherian forms where objects are themselves mathematical structures, but one can also make it a primitive structure where we can view a single lattice as a Noetherian form. So that's the case when the ground category, the category C, the codomain of the functor is just a single morphism category. Then what happens there is that if the ground category is a single morphism category, 2 and 3 will all these three conditions will actually trivially hold because F will now be just identity morphism. And so direct image and inverse image along identity will just be A on the left side, and the kernel of F will be the bottom subobject. And so this will also be A and so on. And so the only thing is the orient part. And so we said that sub X must be bounded lattice. So no wonder. And the Galois connection will also be trivial because it's just identity morphism. So it's no wonder that we get a lattice when the ground category is a trivial category. But we can also generalize this a bit more. Something could be called a stacked lattice. So for example, if in the ground category, we take the category whose objects are natural numbers and morphisms are just the order relation. So this is a poset downstairs here, the poset of natural numbers. Then it turns out that the domain category is also a lattice, provided we require that in this form, every morphism here in the category is an embedding. Then the top one becomes automatically a lattice. And this lattice has kind of layers, right? The fibers, the subobject posets for each object. But then they're also connected with each other. So what are these morphisms that connect them? These are nothing but the realization of direct images. So for example, if I take this subobject of number 1, I take its direct image, that's this one. And this is the relation telling me that the subobject is less or equal to along this map of its own direct image. So we have a lattice upstairs, which consists of these layers of lattices, and but altogether it is also a lattice. And then in this example, the normal subobjects will be just the bottom elements of each of these lattices, and the conormals will be the ones that came from the left side. So the yellow ones are the conormal ones. We'll come back to this example towards the end of the talk. For now, we will just leave it there. So the point was to say that the Noetherian forms, there are plenty of them, actually. And let's see now what we can do with the Noetherian forms. So this brings us to the second part of the talk. which will look at the question, what can be proved in a Noetherian form? Okay, so the original purpose of Noetherian form, as also the name suggests, is to prove the isomorphism theorems. And basically we can prove all the isomorphism theorems there. I haven't encountered a single isomorphism theorem that I couldn't see how it could be proved in the Noetherian form. Here we just look at one example, the Zassenhaus lemma, the so-called butterfly. One should perhaps remark that one of the interesting things about working in Noetherian form is that because the context is self-dual, unlike the classical context of non-abelian group-like structures, some of the proofs would have to be slightly adjusted. And in some cases, completely new proofs developed. And in some cases, it's a wonder that the proof can be found. We'll come to that in a moment. So this proof of the Zassenhaus lemma, even though it's one of the lemmas that has so many different proofs in the literature, appears to be a new proof. So that's the proof suggested by the Noetherian form approach. So basically, let me first remind you what the lemma says. What it says is that if I've got certain subobjects of a fixed object G, so there's only one object G, everything is its subobject, and we have these normality relations. Okay, now I haven't defined what it means for S prime to be normal in S. That's easy. So if S is conormal, and we do want it to be conormal when we write this relation, we can consider the embedding of S into G, and then S prime can be, we can take the inverse image of S prime along S. And once it's here, we can ask it to be normal in here, in this object. And then take the corresponding projection to eventually get this quotient object. So that's what this relation means. It means that if I take the embedding of subobject S seen as an object, right? Then after that, I take the inverse image of S prime along that embedding. What I get here will be a normal subobject. And that allows me to form the quotient as well. So writing this relation is equivalent to saying that this object is defined. Okay, so we've got, the data has that, we've got that, so we've got this defined. We also have that, we've got the other one defined. Then we want all of these actually to be conormal, and we further want this to be conormal and that to be conormal as well. And then, if these conditions are satisfied, then the statement of the theorem is that these ones will also be defined. So they're shown here. So that's this one. So the other one too. And moreover, there is an isomorphism between them. Okay, so the question is now how to find this isomorphism. And what you do in a Noetherian form when you want to prove an isomorphism theorem, you basically want to find a zigzag connecting your objects. And then this zigzag is going to induce an isomorphism when it satisfies a certain condition. We will come back to that in a moment. In this specific case, the zigzag that will do the work will be the one that connects this one with another quotient which didn't feature in the formulation of the Zassenhaus lemma. So familiar proofs of Zassenhaus lemma decompose this lemma into two sub-theorems saying that this object here is isomorphic to that one, and separately that one is isomorphic to this, and then by composing those isomorphisms we get this isomorphic to that. Now this picture will show why we need to go via this. So it turns out that if I take this zigzag, that will not give me an isomorphism. So that's the shortest zigzag I could take connecting these two. But if I take this one, which is not the same as taking this one, even though the diagram commutes, this one is the right one. And so that will give me an isomorphism here, and I will get by duality, well, not by duality, sorry, by symmetry, I will get isomorphisms here as well, and then I compose them. Now, what do I mean when I say that a zigzag gives rise to an isomorphism? So what we need to do in a Noetherian form to check that there is an isomorphism here, once I've identified a zigzag, is something very simple. I need to take the smallest subobject of my object, the bottom subobject, and then kind of chase it along the zigzag. So take its inverse image, then direct image, then inverse image, direct image, inverse image, direct image. And here I need to arrive to the bottom subobject as well. So this needs to happen for the bottom subobject in this direction. And also for the top subobject, if I start with the top subobject here and chase it along the zigzag, I need to arrive to a top subobject here. And the same should be true when I go backwards, when I chase 0 and top, bottom and top backwards along the zigzag. So if these conditions are satisfied, then I can be sure that there will be an isomorphism between them. And as to why this is so, we will come back to that in the next slide. So one can check that in this case, these conditions are satisfied, and that's how one gets isomorphisms there and there, and hence one proves the Tassenhaus lemma. Now, of course, Tassenhaus lemma is needed for Jordan-Hölder theorem, so we have Jordan-Hölder theorem in this context as well. Moreover, the Jordan-Hölder theorem is usually stated, well, the classical one is stated for normal series, right? But there is also Jordan-Hölder theorem for chief series. And this context of a Noetherian form allows us to see that, in fact, the two are dual to each other. So if we take Jordan-Hölder theorem for normal series and we dualize it by formal duality, by that functorial duality, we will get nothing other than Jordan-Hölder theorem for chief series. And so we don't need to prove these theorems separately. We can just have one theorem and get the other for free. And that's the nice thing about Noetherian forms, that this duality allows you to do such magic kind of tricks where you dualize one theorem and get the other one for free. The classical place where duality has been used a lot for proving homomorphism theorems are the homological diagram lemmas. So what we have here on the left side is an example of a diagram lemma of homological algebra. It's the snake lemma. I'm going to state what it says in a moment. So for abelian groups, this can be proved by using duality, thanks to the fact that abelian groups form an abelian category. But for non-abelian groups, it's not possible, because non-abelian groups do not form a self-dual axiomatic context. But now it is possible, you see. So with Noetherian forms, it becomes possible to use abelian type of self-dual arguments also for non-abelian groups, and that's one of the nice applications of this. Okay, so let's see what the snake lemma says. So we need to have a commutative diagram like this, where the projections are indicated with these double arrow heads, and the embeddings are indicated with the arrow tails. And then we also want, apart from this diagram to be commutative, we also want every sequence, either horizontally or vertically, to be exact. And if I have a sequence like this, it's exact at y when the kernel of G is equal to the image of F. And so we want that exactness condition to hold here and here for the vertical sequence, also there and there for the middle column, and for the last column here and here, and also there and there. So practically everywhere where it's possible to state it. And then the lemma says that there is I'm sorry for explaining something that maybe everybody knows. The lemma says that there is a connecting morphism, so something going from here to there, such that this composite, I mean, not the composite, sorry, such that this sequence is an exact sequence. And so there are two parts to the snake lemma. The first one is to produce this connecting morphism, and the second one is to prove that the entire sequence is exact. And as I said before, for abelian case, because one can prove this in an abelian category, one would only need to prove exactness of the long sequence here and there, and then by duality get it here and here. But if one wants to prove a snake lemma for non-abelian groups, then one would have to do it at all of the 4 spots. But not anymore, because in a Noetherian form, duality works, and so it's only sufficient to prove at the top, for instance, or the bottom. And the reason how we get the other one by duality is that if you imagine reversing all these arrows, then you could rotate this diagram by 180 degrees, and then it will match onto itself. So whatever you proved there will now become a proof for here and here. Okay, so proving that this long sequence is exact is not very difficult. there is a little technicality that arises there, but more interesting is seeing how we get this homomorphism. And it turns out that to get a connecting homomorphism here, it's kind of a similar procedure as you would want when you want to get an isomorphism in an isomorphism theorem. And the procedure is the following. So now I'm going to make what I said before a bit more explicit. So if I've got a zigzag of morphisms like this bottom row here, that satisfies the requirement that if I take the bottom subobject of the initial object here, and I chase it all the way there, which means take direct image here, then inverse image here, then direct image, then inverse image, then direct image, I should arrive here at 0. And the same backwards, but for the backwards, I want the top subobject to behave that way. Inverse, direct, inverse should give me top here. So if there was indeed a connecting morphism, right? Because of the Galois connection story, in a Galois connection, left adjoint always preserves bottom subobject and right adjoint always preserves top subobject. So if there was a morphism that would behave with subobjects the same way as the zigzag does in terms of chasing them, then 0 would indeed map to 0 this way, and 1 would indeed map to 1 backwards. So what we're now saying basically is that if a zigzag has this feature, then there must be a connecting morphism, along which chasing is the same as chasing along the zigzags. Okay, and that's useful because here, going back to this snake lemma, when I want to prove that the sequence is exact, I will be chasing subobjects along this zigzag, because chasing along that will be the same as chasing along the connecting morphism. Okay, so now how do we get the connecting morphism when these requirements of chasing 0 and 1 are fulfilled? And the proof how to get that for groups would be quite trivial, because you basically take the composite relation and you get convinced that the composite relation is actually homomorphism. But in a Noetherian form, because of various things that don't carry over there, because we want things to be self-dual there, so relations don't work very well with Noetherian forms, we need to get a different kind of proof. And so this is a completely new argument that was not needed in any other previous context, but now here it's needed and it works. So the procedure is the following. We begin with a zigzag, and then we decompose each map by projection followed by injection. So that's one of the axioms that we had for a Noetherian form. So this is the quotient of the kernel and inclusion of the image. So we do that for every morphism, and we get this triangular situation. Now it will happen so that the orange maps, the embeddings, will always be in the same direction going towards our initial object there, and the green maps, the projections, will always be going outwards. So by the axiom that meet of conormal subobjects is conormal, we can take the meet of the images of these, and that meet will give rise to another subobject here, another embedding here, which will factorize through each of these, and it will turn out the factorizations will also be embeddings. So we get this, this diagram, which will actually be a pullback. And the dual construction by taking join of the kernels of these will give me a push out here. So we do pullback, push out, pullback, push out. And then after that, we compose these maps to get the white maps. And now we will be in a situation which is similar to what we started with, except that the zigzag is now shorter. So now we repeat the same procedure where we decompose these map into a projection. I will first draw all the projections into a projection followed by an embedding. And then do that pullback push out thing once more. So intersecting subobjects and joining the normal subobjects and intersecting the conormal ones. Then once again, I get just an arrow here. And then I decompose that further. And I'm going to get that. Okay, so after this, one proves that no matter what subobject you start with here, A, even if it wasn't 0, chasing it horizontally along in fact, along any path in this pyramid is invariant of the path. So it turns out that chasing in any way, if you go from one spot to the other horizontally, it's always the same result. So that's nice because it means that chasing along this zigzag is the same as going up and then down. And then because we assume that chasing 0 goes to 0 and chasing 1 goes to 1 backwards, it will turn out that chasing 0 that way always goes to 0. And this will force the morphisms that are, and also the same for the other way. And this will force the morphisms that have wrong direction, like these ones, to be isomorphisms. So these morphisms will turn out to be isomorphisms because of this requirement. And once these morphisms are isomorphisms, then I can just compose. I can just compose all the morphisms along this path, because now the morphisms in the zigzag that were going the wrong way, they turn out to be isomorphisms, so I can compose them. And this connecting morphism I'm looking for is nothing other but that this composite. And so that's how one, I mean, that's the sketch, of course, but that's how one gets the so-called homomorphism induction theorem. And if I want this to be an isomorphism, this morphism, then I also want to start with an assumption that the same happens with 1 and 0 and the other way around. That will force another connecting morphism here, which turns out to be inverse of the original one. So this canonical morphism is an isomorphism. So this pyramid basically holds the key to all the isomorphism theorems and all the diagram lemmas that require a connecting homomorphism in homological algebra. So these are the kinds of things one can prove in a Noetherian form. So once again, I don't know of any diagram lemma of homological algebra that's stated purely in terms of exact sequences and that cannot be proved in a Noetherian form. Now here's another sample proof, modularity. So we know that the lattice of normal subgroups of a group is modular. In general, lattice of subgroups is not modular, so we don't have modularity in general. However, we do have modularity when we ask some normality and conormality conditions. So if B is normal and C is conormal, and for groups conormal just means nothing, it means it's just a subgroup, then this equality holds. But there is also another case when this equality holds. This is when B is conormal and A is normal. And in fact, this other case turns out to be the dual of the first case. And it's kind of shown here how we get one from the other by duality. Duality will reverse the inequality and the join becomes meet and so on. And then by rearranging terms, we get expression which was the same as the original one, except that A and C are swapped around. And duality gives conormal out of normal and normal out of conormal. So that's how 1 becomes 2. Okay, so let's try to see how this can be proved in a Noetherian form based off just from the primitive axiom. So all the other theorems will require some theory to be developed before they can be proved fully. But this is an example of a theorem which does not need anything apart from the axioms explicitly. Okay, so here is the proof. So we start with A join B meet C, and with the assumption that B is normal and C is conormal, B will be expressible as kernel of some G and C will be image of some F. Then we notice that because C is bigger or equal to A, in fact, A is equal to A meet C. And so we can replace A with that. Okay, now after that, recall these are the join and the meet formula we gave in the definition of Noetherian form. So this expression here, by the meet formula here, can be rewritten as inverse image of kernel of G and then direct image of it along F, right? So this becomes that. Well, in a Galois connection, left adjoint preserves join, so we can take the F out. So here we just took the F out from the join. Then we get this line. Now think of kernel of G in terms of what it stands for. It's the inverse image of 0 along G. And then use associativity rule. So inverse image of 0 along G and then along F is the same as inverse image of 0 along the composite GF. But then that's nothing other than the kernel of the composite, of course. Okay, so now what we have here is join of AF with some kernel. And now we can use the join formula to rewrite this as, we are keeping the F outside there. We're not doing anything with the F yet. So we can rewrite this whole thing as direct image of AF along the composite and then inverse image. And then again, we use associativity to deconstruct this composite into first taking inverse image along G and then along F. Okay, so what we have now is, now we go back to this original F we had outside. We have now inverse image along F and then direct image along F, and that by the meet formula is the same as meeting this, whatever is inside here, which is this, with the image of F. So that's how we get this line. Okay, so again, associativity is used here. So think of this term. We take its direct image along the composite. So we could take direct image along F and then along G. So that's how we get this line. And then again, we have A, whose inverse image is taken and then direct image is taken. And by the meet formula, this is the same as A meet image F. And then we have, what else do we have there? We have A meet image of F is the same as A, because remember, image of F is C and A is less than C. So we can just replace that with A. And then we left here with GA, so direct image of A under G and then inverse image. And so that's the join formula. We can use that to get a join kernel of G, and kernel of G was equal to B. So substituting it back and C was image of F, we get what we wanted. So it's a few steps, but obviously one could have written this out in a shorter way by applying several steps simultaneously. But it's a nice illustration of working directly from the axioms. We didn't really use any complicated facts about Noetherian forms. Okay, so these are the kinds of things one can prove in Noetherian forms. Basically, homomorphism theorems can be proved there in a self-dual context, and duality is useful for getting two theorems out of one. This brings us to the third part of the talk. And at this point, if I may ask the chair to remind me, when did we start? Because I think we started a bit late. I'm not sure exactly when.
Okay, I don't know who's the chair, but I will speak. That we started about 1, maybe a couple of minutes after 1, and it's now 1:44, so 10 minutes.
Great.
Does that sound okay?
Thank you. Yeah. So which varieties have a Noetherian form? Okay, so I'll make a remark here that this formula alone gives this multiple condition for a variety, but this is when we require this formula for the form of subalgebras. So it turns out to be equivalent to that. This multiple condition is a multiple condition for protomodular varieties in the sense of Dominic Bourne, and the multiple condition was found by Dominic Bourne and George Janelidze, my father. The one implication there is quite, I mean, it's not difficult to establish the equivalence, a standard technique of characterizing conditions by multiple conditions. So we just take the homomorphism F from free algebra of 2 generators to 1 generator, mapping X and Y to Y. That's the F to which we apply the formula. The subalgebra A is the free algebra Y generator. And then, of course, if we take F of A, direct image of A under F, and then inverse image, it's going to be all of the free algebra of 2 generators, because this F is basically a section of the inclusion of A, right? So the image of A under F will be all of the codomain, and then its inverse image is all of the domain. And if we force now this to be equal to that join, it means that every element in here lies in there, in particular X lies in that join. So now X becomes expressible in terms of generators of these two subalgebras, and A is generated by Y, and kernel of F is generated by binary terms that map to 0. Well, to a certain constant, because kernel of F, remember, it is the inverse image of the smallest subalgebra, and smallest subalgebra is subalgebra of constants. So these D terms are the elements of the kernel of F, And then because X is inside the join, then X must be presentable as a combination of the D terms and the term Y, the Y coming from A. But this formula alone is not enough. We also want other axioms, specifically, for instance, the join of normals to be normal and so on. So in the pointed case, when there is only one constant, then this is a characterization. But if not, then it's not quite a characterization. But in any case, we can see that these are very much group-like structures because we kind of think of D as difference and P as an addition. And so the question is if there are other kinds of Noetherian forms over varieties. If there are, they cannot be forms of subalgebras because these forms are kind of this kind. So with Francois van Niekerk, we eventually managed to, I mean, originally my thought was that it's impossible to always get a Noetherian form. That seemed like a crazy idea because Noetherian seemed to be very much related to group likeness, and how can any variety be group-like? But then with Francois van Niekerk, we managed to find a Noetherian form over sets, which then by pullback gives Noetherian form over any variety of universal algebras. I'm going to describe it here. So if you've got an algebra X, its subobjects are pairs consisting of an equivalence relation E on the algebra and either an equivalence class for this equivalence relation, one equivalence class, or the empty set. So A is either empty set or one equivalence class. We could also take A to be just any set of equivalence classes. It'll give a less economical but still Noetherian form. And then in this Noetherian form, the normal subobjects will be exactly congruences. So they will be given by pairs given by congruence in the empty set. So that's when we choose A to be empty. And the conormal ones will be given by subalgebras. It will be given by subalgebra and the equivalence relation generated by it. So A bar is no longer a congruence. So it's a nice form where both congruences and subalgebras live together. And it turns out to be Noetherian. One unfortunate thing about it, well, okay, so let me first say a positive thing about it. The isomorphism theorems for general algebras in any variety can then be obtained through this Noetherian form. By applying the general isomorphism theorems in Noetherian form to the specific one, we can recover the isomorphism theorems for universal algebras in general. However, the sad news is that the homological algebra lemmas are not so interesting because in the homological algebra case, exactness is defined as kernel of a map being equal to the image of another one. And so this requires there to be sufficiently many objects which are both normal and conormal, because kernel of G means normal and image of F means conormal. So if they're equal, it's an object that's both normal and conormal. And in this example, there are not so many objects which are both normal and conormal. So in fact, the normality forces A to be empty set, and then conormality forces the congruence to be the equality congruence. And so it's just the bottom subobjects in each poset that are both normal and conormal. So all homological diagram lemmas in this specific form trivialize. Not in this one where we take form of subalgebras, but in this one where we take the form I've been just describing, they do. And so an interesting question is if there are other Noetherian forms of varieties where homological algebra lemmas would be more interesting than in this specific case. Now the remaining parts of the talk are rather short. So in the fourth part, I wanted to show an example of some combinatorics that we can do with Noetherian forms, but I don't think that we have time for that. So I'm going to skip that. It basically derives from that example I told you about stacking lattices. One can start counting, one can first of all iterate this process by, yeah, I'm not going to go into the detail. There's some kind of way of deriving a new Noetherian form out of the given one, and one can iterate it infinitely. And then in each case, one can start counting the number of maximal chains in these lattices, and they turn out to be very interesting and sometimes very hard combinatorial numbers to count. So the n factorial is for the hypercubes, and the one iteration of that by stacking hypercubes. So these are the lattices given by that, then that, then that, and so on, are given by the odd double factorial numbers. And we don't know what happens in the next iteration. And it seems to be a very hard problem to figure it out what happens in the next iteration. Okay, so let me now go to the last part of the talk, which is also going to be very short, a bit of history. Now, this one is a very difficult one to prepare because there's definitely much more needs to be said here than I can fit it in a short slide. So I will just say that I will just make very few remarks. First of all, a good description of history is given in this paper, duality for groups in the universal isomorphism theorem in a series, duality for non-abelian algebra 4 with Amartya Goswami. The other thing I want to say is that I've found a few references which talk about Noether's project of set theoretic foundations of group theory. Colin McClarty writes in all these papers that what Noether wanted is to get rid of elements and just have theorems in terms of homomorphisms and cosets and sub-objects and so on, subgroups and so on. So what we do here with Noetherian form seems to be very similar to what Noether wanted. Orr was also working in that area. There was a series of papers he wrote in Foundations of Abstract Algebra, which later led to, of course, everybody knows this, to study of algebraic structures, specifically groups in terms of subgroup lattices. Then there is MacLean's paper, Duality for Groups, where he almost did what we're doing here with Noetherian forms, except that he did it in the abelian case, and that gave rise to the notion of an abelian category. And then there are two non-abelian generalizations of abelian categories given by Grande's exact categories and semi-abelian categories in the sense of George Janelidze, Laszlo Marchi, and Walter Tollin. And what Noetherian forms do, they bring these two generalizations together. So these ones, the semi-abelian categories, they include group-like structures, but this context is not self-dual. This context is self-dual, but it does not include group-like structures in the best possible way. And I came across the ideas of Noetherian form by trying to compare these two things. And I noticed that one could keep the good parts of both and kind of put them together like that. And there is also a written summary of the talk that I put a link to on my website. So that will be all. Thank you very much. Oh yes, by the way, just one more thing to say here. I didn't mention Alexander Grothendieck, but I should have, for many reasons. One of them is this quote: "If there is one thing in mathematics that fascinates me more than anything else, and doubtless always has, it is neither the number or size, but always the form."
Thank you.
Thanks.
I have a question. I just want to make sure I understand the Noetherian form that's defined on the variety of sets. So it's a pair, which is an equivalence relation and an equivalence class, a selected equivalence class, or the empty set, right? And this A bar, now you're moving away from sets, but to something enriched over sets, I guess. So that it's a congruence.
No, A bar is still an equivalence relation generated by A. So it's the equivalence relation which has A as an equivalence class, and all other classes are singletons.
Okay, that's what I wanted to check. I just wanted to make sure that's what I understood by A bar, is that it's the equivalence relation with A as a class, right? A is the class and the rest singletons, yeah. Okay, thanks. Anybody have any comments?
Yeah,
Charlotte?
I had a couple related questions / comments. So first of all, thanks for the talk. And I guess just back at the very beginning, I was wondering, so when you first started describing associating to each object in your fixed category C, some poset of things that you think of as some generalized sub-object poset or lattice, as the case may be. To me, at first, it sounded like what you were going to say is that you wanted to look at a functor from the category C into the category of posets, so that each morphism of your objects from one object to another in C induced some sort of isotone map from the corresponding generalized sub-object posets. Is there a reason that that's not what you would prefer to say, or is that definitely not equivalent to what it is that?
It's definitely equivalent, except that it's not really the category of PALS sets with morphisms being monotone maps. The morphisms are rather connections, so they're kind of relations satisfying this property. That if A is less or equal to B and it's related to C and C is less or equal to D, then implies that A is related to D. So if you take these kinds of relations as morphisms between PALS sets, then it is still not quite a functor because we only have implication in one direction, but one can kind of think of it as a kind of pseudo functor. If we go to the Orion form where we take lattices and Gallo connections between them as morphisms, then that will be a genuine functor. And the link between a functor like this and a functor like this is by a famous Grothendieck construction. So we can transition between these two kinds of functors. So you're quite right. This is another way of thinking about it. And the reason why I want to think about this way is because of the duality. It's the easiest to describe.
Oh, okay. So, all right. Thank you. That makes more sense to me now. And so the next thing I'm going to say isn't as related because it's not actually in general equivalent to having a functor from C to posets, as I would usually think of that category. But I know that there has been, over the last 10 years in representation theory, people studying the theory of FI modules and FI things in general. So like, for instance, this paper that I'm going to post in the chat right now has, I think that's the first time that someone analyzed functors from the category of finite sets with injective maps between them into the category of posets. So when you have your picture of an indexed family of like the cube posets, for instance, that's actually an object that those people take as a standard example. And so they also end up employing the techniques of homological algebra to study combinatorial quantities like the ones you listed at the end of your talk. Except the way that they accomplish it is they take some indexed family of combinatorial objects like that, and then they send that to a functor from this indexing category into modules, and then that's an abelian category, and then they do homological algebra. So
wow, thank you very much. I'll take a keen interest to look at this. Thank you so much.
Yeah, I mean, I guess I shouldn't have assumed that, you know, for all I knew, you already knew all of that, but
no, I don't know at all. No.
Okay, cool. Yeah, thanks again.
Thank you.
More questions? Okay.
So you mentioned you had a write-up of this talk on your website. Is it?
Yes. So there's a summary of the.
Link it on the seminar website.
I'll do that. So yeah, please. Yes, of course. Yeah, that will be fantastic. Thank you. Yes. Thank you so much.
Okay, then I'm going to just mention the talk for next week, which is by Erkko Lehtonen. And the title of his talk is Associative Spectra of Graph Algebras. And so you're welcome to join us again next week. Okay, thank you. Let's clap again.
Thank you very much. Thank you.
Thank you, Zurab.